Okay, let's take a look at the results for the exam. I don't know how well you can read this, but what's not up here is the average. The average was 79, and the standard deviation was 17 points. So that just means that most people were within 17 points of 79. Plus or minus. It went really well, I think. That's a pretty good average. You can see here we had several grades over 100, and you might be asking yourself, how did it get over 100? And that is because there was a bonus question. So that's how that happened. Well, we had 6 A's, 6 B's, 6 C's. So this is actually, I have not seen this in quite some time. I have not seen a distribution that looks like that. That's, no, it's I never see that. What I usually see is this. So this is actually a good thing to see because it means, like when I see something like this, I get a lot of students that do well and a lot of students that don't do well, and not much in between, and that's always bad because that means I have two groups in the class, and well, that's the way it is. So this is pretty good. There's room for improvement for some, but some of you are doing real well. Now I will say this first exam is kind of that first, like, let's get this one out of the way. You have a little bit of an idea of how I test. But I believe if you look at most of the problems, these problems were actual homework problems, like exact homework problems. That won't happen again, okay? The lesson in this was if you did your homework, you got a good grade, okay? So on the next test, I assure you, if you do your homework, you'll get a good grade, but you still have to expect that the problems are going to be a little different than what you've seen, all right? So if you didn't do well on this test, you have to ask yourself that question, like, the problems that you were given were homework problems. Like, there's something needs to change if you're in this group here, because I can't do more than just give you homework problems on a test. That's so. Okay. Any questions? I do need to recollect these from you. I already put the grades in, but I do need to take them back. So I just need to look at one thing. Yes. No, I didn't. I actually forgot about it. I graded the exams last week, and I was like, all right. And I had my pre-calc class, I graded theirs. I was like, I'm done. And then I realized this morning I didn't grade that. So I'll get that for you. Okay, do y'all want to turn those back in now? Or I'll give them back to you. I'll give them back to you next class. All right? So if you could, just kind of pass them over and let's try and get them all over here. So the good news here, I think, is that, for a lot of you, you're starting off, thank you. You've got a good start here, right? That first test. And, you never want to start out in a hole trying to dig yourself out. So I'm cautiously optimistic here. All right. Close, come on. What's going on?
This next exam is going to run 2.2 to 2.7?
I believe, if that's what the schedule says. Okay, so we are going to continue. We are still in 2.2?
Yes, sir.
2.2. Where did it go? There we go. Yeah, we're still in 2.1. We're still in 2.1. There's a couple of ideas that I need to discuss here. So I'm gonna try and go quickly through this. Since you all did so well, you understand this, obviously. So I want to go back to the picture that we started with when we were talking about the derivative. And what we did was, the idea was to try and figure out what the slope of the tangent line was here at A, right? That was the whole idea. Try and figure out what the slope of that tangent line was. So what we did is we picked another point over here, and we called this point a plus h. And then what we did is we said, well, the derivative, which is the slope of the tangent line, will be equal to the limit as h approaches 0 of f of a plus h minus f of a, all of this divided by h, right? That was the formula. Now, we've seen that when you use this formula, the algebra can get a little messy, right? You can have some, problems when you plug in a plus h. You get some complicated expressions. In the exam, I think, oh no, that was just a limit. I take that back. There was a limit where you had to do something cubed. I think it was like 2 plus h cubed. So you had to expand it, and that can be a little messy. But we've seen that this can be, problematic. Well, there was nothing that told us that we had to use a plus h right here, right? We kind of did it, and it made sense. We let h go to 0, and that slid this point over, right? But there's another way you can approach this. And instead of using a plus h, we can switch that out for something like, I don't know, x. Just call it x, all right? And then what we want to do is we want to somehow slide this point over to a. So instead of letting h go to 0, what we're going to do is we're going to let x approach a, all right? And we'll have the same effect, won't we? We'll still slide this point over. So what happens is that our formula changes, and we do limit as x approaches a instead of h approaches 0. And then what we do here is we try and figure out what were the ordered pairs. So if I'm plugging in x here, the ordered pair is x f of x instead of a plus h f of a plus h. And then this ordered pair stays the same. This is still a f of a. And then when we do that difference quotient, when we do the rise over run, what would we get? So what would our change in y be here? y2 minus y1, what would it be? F of x minus f of a. And then over, now the difference in the x coordinates. So that would be this minus this, which would be x minus a. So what I'm telling you is that these two formulas are equivalent. But the limits are different. Here you're letting h go to 0, right, in figuring out what happens. Here you're letting x go to a in figuring out what happens. Now look, if x does turn into a right now, if I did direct substitution, I replace that x with a and that x with a, I would get 0 over 0, wouldn't I? And then we're going to have to do some algebra to get around that. So that's what the first part of today is about, is that we have a new formula for the derivative. There are two commonly accepted formulas for f prime of a, and here they both are. We've worked with this one, we have not worked with this one. So what I'd like to do is do an example, and I'm going to show you both formulas with this single example and just kind of compare like which one you like better, okay? You're free to use either one, all right? In fact, someone emailed me or texted me about, can I use this formula? Was that? No, it wasn't? Okay, might have been my online students. Okay, so let's do an example. So let's take, as an example, let's look at the function f of x equals, let's go x cubed minus 2x squared. Let's just do that. And let's find f prime of a, which is equivalent to me asking you for the slope of the tangent line at a, right? So let's use the first definition. Let's use this one. Okay, so using that one there, we'll have f prime of a is the limit as h goes to 0. Now I'm going to just replace all my x's with a plus h's, right? And I get a plus h cubed minus 2 times a plus h squared. That's what happens when I plug in a plus h. And then I subtract from that f of a. Right? Okay, so I'm going to do my subtraction, replacing the x's with a's. So minus a cubed plus 2a squared. Where did that plus 2a squared come from? Yeah, I already took into account this minus was going to go and hit this thing. And since this was positive and this was negative, it switched the signs over. So I did that step already, all right, just because we've done some of this algebra. And now I have the pleasure of expanding all that, right? I get to go ahead and try and expand this. So to save some time, I'm just going to expand it in my head, assuming that you could do this on your own given enough time, right? So when you expand a plus h cubed, you get a cubed plus 3a squared h plus 3ah squared plus h cubed. So that is the expansion of this right here. Then I'm going to have minus 2a squared minus 4ah minus 2h squared. So what I did there is I expanded that in my head, okay, and then I distributed a -2 through. So is that all right? You trust that that would turn into that? Again, I'm just trying to get through this so we can see both versions. And then I have minus a cubed still and plus 2a squared. Then all of this over h. Okay, I'm going to need some more room. All right, what happens here? This becomes limit. H goes to 0. I should have some good things happen here. I've got a cubes gone. What else goes away? 2a squareds. Those are gone. Anything else that I can get rid of? That look good? We good? Okay. I'm also going to, again, try and speed things up here. I know that I'm going to be able to factor an h out of the top. I can pull an h from here, 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 and here, and then I'll cancel it with the h on the bottom. So I know that this h squared is going to become an h. That h is gone. That h cubed becomes an h squared. That h squared becomes an h. This h is gone, right? And then that h cancels. So what am I left with? What's the only thing left? I don't have any more denominator. 3a squared plus 3ah. So that's this, and then I have plus h squared, and then minus 2h. Oh, wait, hold on. What am I missing? I've got this. Sorry, it's Monday. Got this plus h squared. And then minus 4a, oh, there it is, minus 4a. That was that one, and then minus 2h. Okay, maybe I tried to do too much at one time. Okay, do we all agree with that? Now let h go to 0. So when you let h go to 0, it's going to kill off this one, and all you're left with is 3a squared minus 4a, and we're done. Okay? So the algebra was what it was, right? You got through it, right? Okay, let's compare that to the other formula. The other formula, I'll just put right here, limit x approaches a, f of x minus f of a over x minus a. All right, so let's use that one now instead. Let's just see the difference in the algebra and see if we like one over the other. So when we do this, I first have to do limit x approaches a. I know I'm going to have x minus a on the bottom, but on the top I need to put f of x. What's f of x? It's just this, right? I mean, nothing's being replaced. It's just x cubed minus 2x squared. Then minus f of a. Well, that we already did that, right? The last problem also had that. Let me distribute the negative through. What should I put here then? What goes here? Minus a cubed plus 2a squared, right? Okay. Now, remember in the previous limit, the big thing we were trying to get to happen was for that h to cancel, right? Because the h on the bottom gave us the division by 0, and that was a problem. What we actually want to happen now is we want this entire factor of x minus a to cancel. So that means somewhere up top you need to try and get an x minus a in parentheses. And if things go right, It should happen. Let's see. Limit x approaches a. So if I'm going to try and factor the top, and again, I'm trying to factor because I'm trying to get this factor to cancel. So that means I want to try and factor this. If I'm trying to factor 4 terms, what's the common technique for at least attempting factoring of 4 terms? Factoring by grouping, okay? So does that sound familiar? So what we do is we take, there's 1, 2, 3, 4 terms. Right after the second term, we kind of partition our terms like this, and I try and pull a greatest common factor out of both of these. So do I have a greatest common factor here? X squared? And what would I be left with if I did that? X minus 2. Okay, so I'm just working with this right here. Now I move to these two and do the same thing and try and pull out a greatest common factor. But the key is that whatever I pull out of these two, what's left needs to match up with x minus 2 or something like it. Let's see if we can get that to happen. Are we going to be able to do it or no? What could you pull out? Tell me what you could pull out of both of these. A squared. I could pull a positive a squared or a negative a squared, couldn't I?
Positive a squared, negative a squared.
It's up to you. Now let me try something. Let me do negative a squared. What would I be left with? A minus 2, right? All over x minus a. Now, let me try and explain why I pulled a negative a squared out instead of positive a squared. Are there any questions on this so far, though? Yes?
You have x cubed and minus a cubed. Can you use just like difference of cubes? Or like
These two right here do a difference of cubes? Yes. The question is being posed, could I have just moved this a cubed over here and done the difference of cubes formula? Yes, and it would have worked. In fact, I'll show it to you if you want afterward, but this is going to work also, okay? All right, so the reason why I pulled a negative a squared out, the reason I did that instead of a positive, is because I already can foresee the next step. The next step is to write, well, you tell me. I mean, this is factoring, so if you're calculus students, I assume that you can tell me what this is going to become.
X squared minus a squared.
X squared minus a squared in parentheses, right? And then
Minus 2.
x minus 2. Now, do you see why I pulled the negative a squared? What if I would have pulled a positive a squared? That would be a plus, wouldn't it? But I want it to be a minus. Why?
Because you want to get to x minus a.
This is a difference of squares, right? And this is going to turn out to be x plus a times x minus a. See, I saw that at this step, I saw actually at this step, I saw that if I pulled the negative a squared out, that will become a factor, and that's going to break up, and it's going to cancel out this. Y'all see that? Okay, so this is all over x minus a, and this equals limit x approaches a, and now I do difference of squares, x plus a times x minus a, but I still had x minus 2, didn't I? All over x minus a. And you see the factors cancel? Any questions on that? Okay. What happened to the... Oh, wait, hold on. Oh, yeah. Hold on a second. This is go back. This is a complete brain fart. Hold on. This is a complete brain fart. Man, it's Monday, for sure. Hold on. I saw the looks on some of your faces here. Can I write this? Can I write this? I don't know why I did that without even saying anything. Look at this. This is what I said to write. Is that right? Why is that not right? This would be okay if what? If this was x minus 2. But it's not. Right?
No, it's not.
This is not x minus 2, so it doesn't turn into this. So what then?
You have 3 terms on top?
No. You cannot factor this out. Look, if this was x minus 2, which it's not, then what you're really doing on the next step is you're pulling the x minus 2 out, and you're left with x squared minus a squared. But since this is a minus 2, you can't. Right? So you're kind of jammed up at this point does grouping always work?
No.
Grouping does not always work, right? I mean, sometimes it does, sometimes it doesn't. And in college algebra, when it didn't, you just had to try something else, like synthetic division or something like that. Right now, we're not going to go that way here. So with grouping, you can also rearrange terms and try and group, right? You can do that. So I think already this seems a little more like problematic than the previous method, doesn't it? But I don't want you to take this as being, hey, I don't want to use this because look, the first example he gave me is bad. Because sometimes this method's actually easier algebra than the other method. So I think this is an example where it's not, but we need to go back and try and see if we can do this a different way. See if we can go back to this. The grouping of these terms did not work. So let's see here. Sophia had a suggestion. Do you want to re-suggest what you were saying? Difference of cubes. Okay, so you have x cubed. I'm just going to rewrite everything. X cubed minus a cubed minus 2x squared plus 2a squared. I'm allowed to do that, right? Just rearrange? Okay. Now, if I do this, this right here becomes what? X minus a. And then there's a formula for this. So you would have to either look it up or remember it. X squared plus xa plus a squared. Good. That's the formula. And then what do I still have up here? Minus 2x squared plus 2a squared. Okay, so that's my top. Now, you have to be a little careful here, because I agree, this looks like this would go, wouldn't it? This would go, but this out here has to have that same factor also. You can't just cancel one of these. It would be like me doing this. It'd be like me going, okay, take a 2 from here and take a 2 from here. You can't do that unless this one also had a 2, right? That's kind of like, can't cancel that if I don't have one here. So what could I do? Is there any way I could get an x minus a out of that? I could turn it into a difference of squares. So I'm going to have to write another line here. Okay, so let me write this. I've got x minus a, x squared plus xa plus a squared. And then here, watch what I do. Take out a negative 2 and be left with x squared minus a squared all over x minus a. Go. So I pulled a negative out, a negative 2 out of both of these, which changed it to this. And there's my difference of squares. That'll become x plus a times x minus a. I think I'll just write that right above it. Okay. So does everyone see that we now have the x minus a factor in both of the numerator expressions? Now we can cancel an x minus a at this point. All right. So let's do that. We're going to keep the limit. We're not done yet with the limit. So limit x approaches a. When I cancel this factor here, here, and here, I'll be left with x squared plus xa plus a squared. And then minus 2. I still had that 2. And then what's still here? X plus a. And what was on the bottom? 1, right? Because I canceled it. I canceled that factor. So really, I don't need this written as a fraction. I'll write it as a fraction just because it kind of looked like I was anyway. But that cancels, so I have a 1 down there. I did notice on some of your tests that when you did cancel h's that were on top and it was just h left on top, that you didn't put 1 over and that you just would write the denominator. So be careful on that. All right, at this point, we should be able to let x become a and not have division by 0 anymore. So what happens if this x becomes a? So no more limit. It becomes a squared plus, what's this become? A times a, right? A squared again, plus what? A squared. And then minus 2 times a plus a, right? Which is what? 2a. And what does that give you at the end of the day there? 3a squared minus 4a, which is the same result we got the other one, right? 3a squared minus 4a. So be careful, these a's are being added, not multiplied, so that's why it's not a squared. So I don't think I've sold you on this formula being better, have I? I mean, I haven't sold you on this. I'm not trying to sell you on it. I'm just trying to show you that it's different, right? Let me show you one more, okay? One more. Let's take one that was a little more complicated looking, like something like square root of x plus 1. If we wanted to find the derivative, let's just look at the first way, and let's not actually do it. All right, let's just look at the first definition, the limit formula that we had from previous classes. We would be doing limit h goes to 0, f of a plus h minus f of a all over h. That's what would happen if we used the first definition, isn't it? Now let's compare that. So versus the limit, this time as x approaches a, of f of x. What's f of x? Root x plus 1. And then minus, what's f of a? Root a plus 1 all over x minus a. Okay, so those are the two limits that you would have to try and do. What would you do for this one? Conjugate. You'd multiply top and bottom by the conjugate, right? Now the conjugate would be this plus that, right? Over here, top and bottom. Over here, what would you do? Conjugate also, right? And they look almost equal in terms of difficulty level, don't they? Like what it would take. Let's do this one. All right, I want to work this one out just so you have at least two examples of this. I'm going to do root x plus 1 plus root a plus 1. And then I have to do that on the bottom. Root x plus 1 plus root a plus 1. All right, that's me coming in with the 1. That's my conjugate. And then by design, I know I only have to worry about the first and last terms. I don't have to worry about the middle terms at all, do I? Okay, what would I be left with up in that numerator? X plus 1 minus a plus 1, but then that minus would be distributed. So minus 1 like that. And then over x minus a times all this junk over here. And I've told you already, do not try and multiply that out. Okay, don't try and multiply this all through. Are y'all with me? Do y'all see it? What's going to happen? Yep. On the top, right, your 1's cancel. They're gone, right? And so all you're left with on top is x minus a. And that's going to cancel with this x minus a. So you're left with x minus a up here. It cancels with this. You're left with a 1 on top. Don't forget you have a 1 on top. And so one more line before the limit. You have 1 over root x plus 1 plus root a plus 1. And now you're supposed to let the x become a. Right? So if I let this x become an a, I get root a plus 1, right? If I have root a plus 1 plus another root a plus 1, that's 2 of them. So I have 1 over 2 roots of a plus 1. And that's exactly what we would have gotten had we done it this way. Questions? All right, so Now you have two ways of calculating derivatives using the limit. And it's always up to you. I don't care what you do. I think a good exercise for yourself might be to go back and try to do some of the homework problems that you did with the other formula and see how they go with this one. If you really want to kind of get good with the algebra, then that would be a good practice for you. All right. Now moving along. At the end of 2.1, there's a topic that we need to discuss. And it has to do, you could almost say that this is an application. All right here. The other day I was watching a video, one of my lectures, because I was making sure the volume was working or something. I was on my phone. And my wife was sitting next to me, and I was using this as a pointer, and she's like, "What is that in your hand?" I was like, "It's a ruler." She's like, "What?" I don't know, she thought it was really awkward that I was using this as a pointer. She's like, "Is that weird to y'all that I use it?"
Maybe she was associating it with, nuns and being...
I don't know. Okay, so here it is, my pointer. The derivative as instantaneous rate of change. All right, the derivative, f prime of a, not only represents the slope of the tangent line to a curve at a number a, it also represents the instantaneous rate of change of the function at the number a. Instantaneous rate of change. And this goes back to that whole idea. We talk about driving a car. If you're driving your car and you look at your speedometer is supposed to tell you your speed at that instant when you're looking at it, right? But instantaneous speed is troublesome, because when you talk about speed, all right, when you talk about speed, by definition, speed is your change. I'm going to use delta for change. Your change in distance divided by your change in time. So if you go 30 miles in 1 hour, your average speed was 30 miles per hour. But that doesn't tell you anything about your speed at an instant. And the trouble with instantaneous speed is that how far would you go? What's your change in distance in an instant? There's no change, right? And how much time elapses in an instant? None. So you get 0 over 0, right? But that's okay, because that's what we've been getting with this anyway, right? And we've found a way around it. So the derivative gives us the ability to talk about instantaneous rates of change, which is one of the big trouble spots that we had initially, we humans, whatever. Newton and Leibniz, the two fathers of calculus, were trying to find their way around this issue. So we can talk about the instantaneous rate of change of something at a specific point in time. And you can even look at it in terms of velocity, okay? So this is one of the main results, okay? If your function is a function of time, right? We say S is some function of time, is some curve where S is the linear displacement of an object at a time t. So imagine, linear means straight line, right? So imagine you have like a car driving in a straight line, okay? So you're driving, you're slowing down, you're speeding up, you're slowing down, you're speeding up. Then you can plot the time and distance on a graph, and this would be, well, your distance versus time graph. This function right here tells you how far you've gone at a specific point in time. If you look at the end, right, if we start at one point there and then pick some second point, can you all see this okay? Right? Then if I'm looking from this point in time to this point in time and I find the slope of the secant line, that gives me my average speed, my average velocity. But what we want to do, and what we're now able to do, is go to any point in time. At a specific instant in time, we can find the speed, the instantaneous velocity. All right? Now, if you want to do an object that's not moving in a straight line, and you want to do an object that's moving like more in three-dimensional space, then you take calculus 3. You can do the same thing. We do everything that we do here, but we do it out in three-dimensional space. So it turns out it's not a difficult computation. So I think really the only thing I would say for this is I'll show you an example. I won't work the example, but I'll show you an example of the type of problem you might see for something like this. So it would be something like, S equals f of t equals t cubed plus 2t plus 5 is the distance in feet an object has traveled in t seconds. If this is linear motion, then find instantaneous. Oh, I'm totally messed that up. Instantaneous velocity at t equals 3 seconds. So that's the way the word problem might be phrased. They give you some function of time. They tell you that this function represents how far an object has traveled in feet, all right, in feet, after so many seconds have transpired. I also state that it's a linear motion, which means that everything that we've done applies to this. And I'm asking, what's the instantaneous velocity at t equals 3? So what am I really asking for here? F prime of 3, okay? And you would have two options. Actually, you would have multiple options on how to do this. You could do this and find the derivative at a, and then plug in 3 for a, right? Or you could actually just use the formulas and replace the a's with 3's. That would be, up to you how to do that. So I'm going to show you 3 different formulas, actually 4 different ways you could do this. You could do f prime of a and use the first limit definition. You could do that, right? And then after you do that, get an answer, and then you'd plug in 3 for a. I could also do the second definition. And then same thing. Plug in 3 for a when I'm done. The 2 other options that I would have here, since I'm only being asked for the speed at a specific point, is I could come up to this formula and I could replace that with 3 here and that with 3 here, or I could replace that with 3 here and that with 3 here and apply the same 2 formulas, and I would get the answers, and that would be the answer, right? There would be no a's left over to plug in. So those are kind of like your 4 options. Do y'all understand what they are? What's the advantage of doing it with a's instead of the numbers?
Use other numbers.
Later on, if someone asks you to find the speed at a different point, it would be more valuable to you, right? Okay. All right, that wraps that up. I'm not going to work through that one. Let's move on to the derivative as a function. Students seem to have trouble with this concept. I'm not sure why. Let's see how this goes. All right, so up until now, we've been using we've been able to determine the derivative, right? At some value of a, right? You have 2 versions of the formula. Here's that second version, or here's the, why does that say second version? Well, that's the first one I gave you, right?
Well, that's the limit.
Yeah. Yeah. So scratch that second. This is the first one I showed you, right? So we have this formula, right? Okay. The A here was, I just picked A, right? I mean, like I could have called it B, I could have called it C, I could have called it anything, right? So could I have called it X? Sure, I could have called it X. And when we calculated this limit, we should get some answer that has X in it, right? So if I rewrite this definition and I write f prime of X instead of f prime of A using this limit definition, this is what it would look like. And my answer would be some function, right? Something that has X's. So f prime of X would represent the slope of the tangent line of the curve, of this curve, at this point, x f of X instead of A f of A. Agreed? I feel like I need a picture, but same picture. This is X now, this was X plus H, right? We're going to move that point over. So this point right here is x f of X instead of A f of A. Okay, if we do this, and we leave X alone, that is, we don't replace it with an actual number, if we just leave it as X, then our answer should have an X in it, and should be a new function of X. It's a brand new function. So let me show you an example here. Okay. This is a function, little f, right? You see it? That's f of X. Now, I could go and at every point, I should be able to calculate the slope of the tangent line, shouldn't I? Okay, so let's just, I'm picking points, I'm moving, left and right here. The computer's calculating the slope of that tangent line. So right now the slope is positive. And as I move to the right, it's going to stay positive, but what's going to start happening to it right now? It's going to get smaller, still positive, so 2 point something, and then it goes to what? 0. And then it starts going negative, and then it gets bigger negative, and then it's actually going to go back to 0, isn't it? And then let me go back to this side. Here I'd have the derivative would be 0. So what we're trying to get you to understand in this section is that the red function is some function, but the derivative of this red function is a new function. And I could graph it. So what I'm going to do is I'm going to actually bring in, there's my x value, okay? Oops. Okay, so let me try and draw this. So let's take a look right here. What is the slope of the tangent line here? 0, right? Well, yeah, 0.05, but it's about 0, right? So would you agree that f prime of X is 0 at this point, which looks like it's about right there, right? So what I'm doing is I'm going to start drawing a green graph. The green graph is the derivative. So I put a point here at 0. Let me try and do this again. Let me bring that out. Let me come over here and let me go right there. So that, again, my derivative here is 0, isn't it? So I'm going to put 0, up and down 0. And then I'm going to move over here, and it should be 0 here, like this. Somewhere around here it should be 0. Now, when I'm about right here, let's say right about here, let me go to the other side, right there. The slope of that tangent line is about what, 3.43? So the derivative right here should be about 3.43, which would be, here's 2, here's 3, it'd be somewhere around here. Do you agree? If I move this point to the right a little bit, my slope is still positive, but now it's what, 2.45? So about right here, I go up 2.45, I don't know, that pretty good right there? And I can do this for every single x value. Let's see, slope is 0.95 there, so I go up, there's 1, so a little bit lower, something like that. See, if I start connecting all these dots together, I'm going to have a graph, right? So that's what I have the computer do for us here. There's the graph. So you can see that green function is just taking the slope of the value, or the slope of the tangent line as a quantity and plugging it in as the y coordinate for this function. So see, I have positive slope, the slope is 0, now my slope is going to be negative. It's going to be pretty big negative, but it has to get back to 0, doesn't it? So notice these values are all negative values. And then it goes back to 0. Once I get past here, my slope is positive, so my derivative is positive. So what you have graphed there together is the function and its derivative. Do y'all see the connection? This is kind of like a light bulb thing. It either like you click, you see it, or when you don't see it, it's like, what? What's going on here? I'm going to give you another example, but the whole point of this is that for every function, if we can find its derivative, we should be able to graph it. Okay, let me give you one that I think is a little more straightforward. This one, I'm going to just draw the function first, and then I'm going to ask you to help me draw the derivative. So what if we have a graph that looks like this? I'll draw the f function in purple here. This is an interesting function right here. This is f of x. And I'll give you what it is even though you don't need it. That's the absolute value function. Okay? Let's talk about its derivative. So I'm going to do the graph of the derivative in green. So let's pick some point over here. Just pick some arbitrary point right there. What is the value of the derivative at that point? So what is the slope of the tangent line to the curve at that point? Well, it should be negative, shouldn't it? It's actually -1 because this is like the identity. It has a slope of 1 here and -1 here. So do you agree that when I plot my derivative function at this x value, it should have a value of -1?
Yes.
Okay, so that means here's -1. I'm just going to come over here and I'm going to put a dot. Okay? I don't really want that dot there. This point lives on my derivative, right? Now let's pick another point. How about right there? What's the slope of the tangent line there? What's the slope of the tangent line here? It's the same as it was here, right? -1 still? Right? So I should put a point still at -1, right? What if I pick a point right here? What's the slope of the tangent line there? -1 still. In fact, if I pick any point on this section over here to the left of the y-axis, I'm going to get -1, aren't I? And if I were to pick any point out here, my value would be -1. So I can pretty much assume that it's going to look like this, isn't it? Over there? What about over here? If I pick a point over here, what's the slope of the tangent line there? +1. So let me put +1 right there. So I should have about +1. How about if I pick this value right here? Slope of the tangent line there is +1. What if I pick this value here? +1. And it should be that for anything over here. So it should look like this, right? The only thing that's interesting is what's happening at 0. Okay, so let's imagine if we were to pick points here or here or here, this should all be 1, shouldn't it? And this should all be -1. But what happens at 0? Something happens that's not good. I mean, look at this. Your slope of your tangent line over here is negative, right? Until you get to here. And what happens when you get to 0 and move past 0? It goes from -1, what? Instantaneously it goes, switches to +1. It's not like a curve where it smoothly, gradually curves through, right? So this is like a big abrupt change in value. So we are going to have it at 0 be undefined. You do not have a slope of a tangent line at 0. The green graph is the derivative of this function. Y'all understand that? Let's try another one. Yes. Oh, yes. Uh-huh.
Is there any significance with the intersection of the derivative function and the other function?
Any significance?
With like their-
Oh, where they hit each other? Not really.
Yeah.
Not really. But actually, that's actually a really good question. The question that's being asked is this point significant? That would be where the function equals its own derivative, right? That's actually a very good question. I wonder if there even exists a function where this, right now, do you agree with me that this does happen one time? It appears to happen one time, but it doesn't appear that it happens anywhere else. I wonder if there's ever a function that is always equal to its derivative. That means they intersect each other everywhere. I wonder. That would be a pretty awesome function, right? Because what a function like that would mean is that, think about this, this is pretty profound, is that if you wanted to know the slope of the tangent line of this function, all you'd have to know is the value of the function. That's all you would have to know. So like, let me draw you a parabola, okay? A parabola. If I go to the value 1, I have a slope of a tangent line, don't I? This is the function f of x is x squared. Okay. So at 1, what's the value of the function at 1? 1, right? What's the value of the function at 2? 4, right? What we're trying to look at here is this slope of the tangent line equal to 1? Is this slope of the tangent line equal to 4? That'd be pretty cool if everything, like if I went out to 3, the slope of that tangent line was 9, right? Because that would just be the function's value there. Well, it turns out for x squared it doesn't work that way, but there is one function that this does work. It's a pretty awesome function. It's the only function. There's only one that does it. There's only one that exists that does this. It's unique. And we were looking for it for a long time. We were asking ourselves, can we find a function that does this? Can we find it? Does it exist? It does. You've seen it. It's that. That's what makes that function so important. It's the only function that is equal to its own derivative. So when you graph e to the x, we're going to talk about this, all right? But you brought it up. All right, so if we go and we look at that function e to the x, that's what it looked like in college algebra. Turns out that if you go to any value, like 1, and you want to know the slope of that tangent line, guess what it is? It's e to the first power. That's what it is. If you want to know the slope of the tangent line at 2, that's e squared. The slope of the tangent line at 3, it's e cubed. This is a unique function that it behaves that way. It's the only one that does it. Okay, we will get into that later. All right, let's try and do one more of these. Okay, let's see if I can't mess you up. All right, so first I'm going to graph f. This will really kind of test whether or not you understand what's going on. That almost looks like a cosine function, doesn't it? It almost looks like a cosine function. I didn't intentionally make it that way, but it does look very cosine-ish, doesn't it? Okay, let's go to the easy places first. Are there points on that graph where you can tell the derivative is 0? Yes, that's happening, looks like here, 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 right? At these top and bottom points. So here, corresponding to that same x-coordinate, the derivative should have a value of 0 there, right? The up and down is 0. Here, the derivative is 0. Here, the derivative is 0. Here, the derivative is 0. Actually, it's happening there and here, too. Do y'all agree with that? Okay, let's carefully inspect the slopes of the tangent lines. Let's start out right here. So what's going to happen is I come this way like this. My slope is going to be negative. Not very steep though, right? And then it's going to get a little bit steeper, right? Pretty steep. That means it's going to be a pretty big negative number. And then it's going to be still negative, but smaller negative numbers until I get back to 0. That means when I graph this derivative between here and here, it's going to be small negative numbers until it gets to a pretty big negative number, and then still negative numbers back to 0, but smaller. So it's going to look something like that, right? Do y'all see that? Now, when I get to here, what's going to happen is I start to move to this. Slope of tangent line, small positive numbers, then it gets pretty big positive, and then it's going to still be positive, but it's going to be getting smaller back to 0. So it's going to look like small positive numbers to a bigger positive number, then still smaller positive numbers back to 0. Do y'all see that? And you could do that for all of these. Let me go back here. As I move to the right, from here to here, it's going to be what?
Positive.
Small positive to a pretty big positive, then back to small positive. So it's going to look like that. Then the other way. Oh, wait, what did I do? Oops. I was like, that is not right. That is not right. Okay, small positive numbers, back to 0. Small negative, back to... Man, that almost looks like what function? Almost looks like a sine function that's been reflected over, right? Like it almost looks like if this was cosine, right? If this was cosine, which I'm questioning, I don't know if that's really cosine because it's been moved up, all right? So maybe it's like cosine plus 4 or something like that. Cosine x plus 4. This looks a whole lot like what? Negative sine x? Doesn't this derivative look a whole lot like negative sine x? And we are actually going to show that later on, that the derivative of cosine x is negative sine x. But you can see in the picture that it kind of seems like that would be the case. And also notice that the 4 doesn't seem to have factored in, right? So imagine I had taken this purple graph and put it down here. Would you have drawn anything different on the green?
No.
No. So actually moving a function up and down has no impact on its derivative at all. And that's because, as we'll see later, the derivative of a constant is always 0. So when we take the derivative of this function, that part shouldn't matter. All right. Let me give you one more. Instructions are going to be different, though. What's different? This is backwards. I'm giving you the derivative. I'm giving you the picture of the derivative, and I want you to recover the original function. Now, from the previous example, we know that the up and down won't matter, right? What really matters is the shape, the curve of the curve, right? All right, so let's see if I can't do this. Okay, I'm just going to pick some point. What is this x-intercept on my derivative telling me? That the slope of the tangent line at that x value is 0, right? So I know that when I graph my f, right? What should I do f in? Red? When I do this one, when I'm here at 0, I should have a flat tangent line. So I get to pick where I want f. Doesn't matter. So I'm just going to put it here. I know that the slope of my tangent line there should be 0, right? That's all I know about the function. What do I know about when I start moving this way? What is my slope doing? So if I look at that right there, that is a small positive number, right? So on my f function, as I move to the right, my slopes of my tangent line should be, they're positive, but they're getting what? Bigger. So it should be getting larger slope, which means the graph should probably do something like this. It's very similar to what's happening